Good morning, everyone. Welcome to you. I'm going to cover the conjugate beam method, and from this point onwards, I'll be doing another section on statically indeterminate beams and how to analyze statically indeterminate beams. So, conjugate beam method is basically for statically indeterminate beams, or we can use it for statically indeterminate beams as well, that we will briefly discuss at the end of the lectures on statically indeterminate beams. So the conjugate beam method is developed by uh, Otto Moore in 1868, and it generally provides a more convenient means of computing slopes and deflections. I understand that you've been you have been studying about beams and how to determine the deflection of beams and slope of a beam using double integration method in the last few lectures, and this lecture is basically on how to determine slopes and deflections of a beam that using conjugate beam method. It gives you an easy way to develop the slopes and deflections. Although the amount of computational efforts required by the two methods is essentially the same compared to the moment area method, which you have been covered in the last lecture, the conjugate beam method is preferred by many engineers because of its systematic sign convention and straightforward application, which does not require sketching the elastic curve of the structure. So we'll see how can we adopt this method to determine slope and deflection of beams. The conjugate beam is based on analogy between the relationship among load, shear and bending moment, and the relationships among M over EI diagram, slope and deflection. So you can see that this here I'm comparing load, shear, bending moment, which is corresponds to M over EI, slope and deflection. So load is compared with M over EI, shear is compared with slope, bending moment is compared with deflection. So let's see how can we do this. So now if you look at this method of conjugate beam method, what happens is, if you take a real beam, so what you do is, in a real beam you do the analysis and then you can plot bending moment diagram. Say if it is a simply supported one, we can, with a point load, we can have a M over EI diagram, something like that. So this is M. So this is for a beam which has a point load. So if my beam is something like this, and if the W is this, the M is equal to WL over 4. Okay, so that's how we plot bending moment diagram. So this is bending moment. I'm just sketching to show you, because I think you already know how to plot this one. So that is M over bending moment diagram. So now if I divide this bending moment by EI is flexural rigidity of a beam. So if I divide this by EI, since EI is a constant, my M over EI diagram also looks similar. So it will have a similar shape. Let me draw this. Oops. Okay, that looks better. So M over EI. So that is the M over EI diagram. So this is bending moment diagram. This is M over EI diagram. Okay, so diagram. So now what I'm going to do is I'm going to use this M over EI diagram. So for example, if you look at in an actual beam, if you take shear force, the first derivative of the shear force gets you the load, and first derivative of moment gets you shear force. So second derivative of the moment gets you the load. So that is a known, because you have been studying about this for a long time. Now if you look at your previous discussions about double integration method, you have developed this one, d2y by dx squared is equal to m over EI, and you have developed dy over dx is equal to theta, and d theta over dx is equal to m over EI. So you have already developed these, and you can compare this, like, okay, this looks like this, and these two look like this. Okay, so you can compare these two, and when you compare these two, you get some idea. What is that idea you are getting? You can see that if you apply a load on a real beam and you derive a shear, you can plot a shear force diagram, and that shear force diagram is and if you get a shear force value, and the first derivative of the shear force equation gives you the load. So the load in a real beam is similar to m over EI in a conjugate beam. So if you consider m over EI as a load on a conjugate beam, the shear force of that conjugate beam is going to be your slope, because it is d theta over dx. So the shear force of a conjugate beam is going to be your slope. So that's what this equation says. And then your bending moment of your conjugate beam is going to be the deflection. So here you can see that the second derivative of the bending moment gets you the load, and here the second derivative of the deflection gets you the m over EI diagram. So if I compare these two, what I'm getting is what I learn is that if you apply a load, actual load on a real beam, and if you derive an equation for bending moment diagram, then the second derivative of that bending moment equation gives you the load. So similarly, this equation has a similar pattern, so which means that the bending moment of a conjugate beam is going to be the deflection of a real beam. So if you can plot a conjugate beam and apply m over EI as a load on that conjugate beam, then you can work out shear force equations and bending moment equations for that conjugate beam, considering m over EI as the load. In such case, the shear force that you derive for a conjugate beam is going to be the slope of the actual beam. and the bending moment of that conjugate beam is going to be the deflection of the actual beam. So that's what these two sets of equations tell us. Now we'll see how to develop this conjugate beam. To develop the conjugate beam, we need to have some sort of assumption, or we need to have some sort of a methodology to convert the real beam into a conjugate beam. So this is the same thing that I had discussed earlier, that in other words, if you assume M over EA as a load on a beam, the shear force of the conjugate beam at any point will give you the slope of the actual beam. Okay, the shear force of the conjugate beam gives you the slope of the actual beam, and the bending moment of the conjugate beam gets you the deflection of the real beam. So now if I move to the before I move into the next section, now let's take a uniformly distributed beam. Okay, so uniformly distributed load, a beam with a uniformly distributed load. So this is say 6 kilonewton per meter. So let me get the support reaction. So if the span is say say 6 meters, so the reactions are, if the support A and B are A R B, so RA and RB is going to be equal, so RA is equal to RB is equal to 18 kilonewton. Okay, so that is the reaction, and if I take an arbitrary section of this beam, I can derive the bending moment equation. So this is 18, and there's a load acting on that portion. So if I mark this shear force, bending moment, and axial force, so mx, so if you sum all the moments to be 0 at x, so at x sum of all the moment is equal to 0, so that is equal to, that's then mx, if you clockwise positive, so mx minus 18 into x plus 6x into 6x is the load, so this is 6 kilonewton per meter, so 6x is the load acting on this small portion, and the effect is that x by 2 is equal to 0, so mx is equal to 18x minus 3x squared. So this is the equation for bending moment diagram, and if I plot the bending moment diagram, so I'll get a curve like that. Okay, it's the second order equation, so I'll get a curve like that. Okay, so that is my bending moment. Okay, let me add, this tool is a bit tricky to draw. Okay, that's better. So this maximum value is x when x is equal to 3, so when x is equal to 3, it's 54 and minus 27, that is 27, so 27 kilonewton meter is the maximum bending max. So this is the bending moment diagram for that beam. So this is the bending moment diagram. Okay, in most of the beams EI is constant. There can be beams with different EI. Okay, we'll see that in several examples in other problems in the future. So if you consider EI is constant, then you will get a similar shape of the bending moment, not a bending moment diagram, M over EI diagram, as I discussed earlier, and that diagram can be used to work out the conjugate beam. So let me stop here in this case. We'll take this out later in a while. So now if I go down, we have to look at the reciprocals. Okay, so the reciprocals of the support condition. Okay, so the reciprocals are the, how to define the support condition. So for example, if you have a simple end support, okay, simple end support, not the simple support in the middle, but simple end support, so something like a pin or a roller, then in this support you don't have a moment, you have shear force. Okay, so now this is very important, so you need to pay a bit of an attention here. So we are comparing slope of the real beam with the shear force of the conjugate beam, and the deflection of the real beam with the moment of the conjugate beam. So if you look at a simple support, in these supports, either roller or a pin, if they are located at the far end of a beam, at the end of a beam, then there is a slope here. Okay, there is a slope here, but there is no deflection here because it is supported. So if there is a slope, means in the conjugate beam you should get shear force at that support, but you should not get any moment because there is no deflection at the support. So since there is a slope here, there should be some shear force. Shear force cannot be zero in a conjugate beam, and there is no deflection at those supports, so which means there should not be any moment at the support. So if you need a support where there can be shear force but no moment, then it should be again a pin or a roller. So if end support in a real beam is a pin or roller, then the end support in a conjugate beam also will be a pin or roller. Okay, so that is the reciprocal of those supports. Then if the support is fixed, that means you cannot have any slope, you cannot have any deflection here. Means at those supports in a conjugate beam, you can't have moment, you can't have shear force. So if you can't have shear force, if you can't have moment, then that point in a conjugate beam should be a free end. Okay, because at the free end there is no shear force, there is no moment. If it is a pin, then there will be shear force but no moment. But if it's a free end, there will be no shear force, no moment. So if it's a fixed support in a real beam, it should be a free support in a conjugate beam. And if it's a free support in a real beam, which means in a real beam it's a free support. Okay, so that means you have some slope, you have some deflection, means that in the real beam you have moment, you have shear force. So if you want to have a moment and shear force in a support, that support should be a fixed support. Okay, so then if it is an internal pin or internal roller, means in an internal pin your shear force will be there. Okay, shear force will be there, but there will be no deflection. So in an internal pin, internal support, you have shear force, but you don't have any moment, you don't have any deflections. So in an internal support, in actual beam, if you take this two support conditions, there is a slope, there can be some sort of a slope, something like that, or in a different way you can have a slope, but you can't have a deflection here. So which means in a conjugate beam you can have shear force but you cannot have moment. So if you cannot have moment in a conjugate beam, that point should be a hinge. So it's a hinge in a conjugate beam. So if it's an internal pin or roller, means internal hinge. And if it's internal hinge, you can have slope, you can have deflection, means it's going to be internal roller. Okay, because in the internal roller there will be shear force, there will be moment, but the net moment will be zero, but there will be moment. Okay, so it has some moment carrying capacity at this point, but the net moment will be zero. That's a different part we will look at later. Okay, so now we will see these reciprocals and this, in a bit of while. Before that, we look at the sign convention. So the benefit of using conjugate beam method is it's easy with its sign convention. So if the positive ordinates of the MOVA diagram are applied to the conjugate beam as upward loads. So now if your MOVA diagram is on the positive side of the diagram, then you will convert that as a load acting upward. So for example, if I take my previous example that I worked out, so let me copy this, edit, so actions to spin highlighter, let me see if I can. Okay, so if I copy, okay, see, copy. So if I copy this and if I paste it here, okay, so that is my bending moment diagram. So from bending moment diagram, if I plot MOVA diagram, it's going to be on the same side. Okay, so this is the MOVA diagram. So you divide all the values by EI, so it will get a same shape because EI is constant in the case I considered. So now this is on the positive side of the curve, positive side of the graph. So in that case, so this is converted as a load which is acting upward. So now I have a pin here and I have a roller here. So as we discussed earlier, it will become a pin and a roller again, and this is my load. So this is a real beam and this is a conjugate beam. And if I consider this load acting on this beam I have considered, then if I derive bending moment equation, that bending moment equation will give me bending moment values at any point in this beam, and that value of the bending moment is equal to the deflection of a real beam. And if I get a shear force due to this load on this beam, and that shear force is equal to the slope of the actual beam. So here if I find shear force or bending moment on conjugate beam, then it is equal to slope and deflection in real beam. It's very simple. So you plot bending moment diagram and you divide it by EI, and then you derive the MOVA diagram. The MOVA diagram is a load acting on a conjugate beam. So for that load, if you derive shear force and bending moment, that shear force and bending moment is equal to slope and deflection of a real beam. So it's very simple. So if your MOVA diagram is on the positive side, the load is acting upward. If it is on the negative side, the load is acting downward. Then a positive shear in the conjugate beam denotes a positive slope. So if you have a load acting on this direction, and if you derive a positive shear value, that means that gives you a positive slope. So positive slope is counterclockwise direction. So a positive shear in the conjugate beam denotes a positive slope of the real beam with respect to the undeformed axis of the real beam. Also, a positive bending moment in the conjugate beam denotes a positive deflection of the real beam with respect to the undeformed axis of the real beam, and vice versa. So if it is a positive bending moment, you get a positive deflection, means it's upward deflection. If it's a positive shear, your slope is positive, means counterclockwise rotation, counterclockwise slope. So it is very simple, the sign convention when it comes to conjugate beam. Now look at some examples of how to convert this conjugate beam to a real beam, or a real beam to a conjugate beam. So now if you look at this case, you have a pin support here, a roller support here. So in the conjugate beam, it's going to be a pin and roller, as discussed earlier. And if you have a fixed here and a free end here, it becomes free here and fixed here. Why? So here it's a fixed, so means there can be moment, there can be shear force. So in the conjugate beam, that should be a free and a fixed, because in this support you can't have a slope and a deflection. Means slope and deflection of a real beam corresponds to shear force and bending moment of a conjugate beam. So if you can't have slope and deflection in a real beam, that means you can't have shear force and bending moment in a conjugate beam. So if you want a point where you have no bending moment or no shear force, means it should be a free support. And here in this free support in a real beam, you can have a slope, you can have a deflection, means in the conjugate beam you should have some moment, you should have a shear force. So that's the analogy. Okay, so now similarly, if you can see here, it's a free end becomes a fixed here, internal roller becomes a hinge, and external pin support becomes external pin support. And here the fixed support becomes free, internal hinge becomes internal roller or internal pin, and external roller becomes external roller. So these are some of the examples how to convert a normal beam to a conjugate beam. So this is a normal real beam. So real beam pin, end pin becomes end pin, internal hinge becomes internal roller becomes internal hinge, and external roller remains external roller. So the ones on the left side are real beam and the right side are conjugate beam. So these are another set of examples. So where you have real beam, so these are real beams, conjugate beam. So you should be able to having some idea by now on how to define the support conditions and how to assign load to a conjugate beam. So if I give you a real beam, then you will have some idea now how to convert that to a conjugate beam. So once converted into a conjugate beam, we can work out the other details. Okay, so the next slide is going to be a problem. So let's discuss this problem so that you can understand it better.